Hi class, welcome back to the continuation of our lectures in quantum mechanics, and this is the fourth lecture on chapter 5. And I'd like to remind you again that our main reference for this lecture is the Introduction to Quantum Mechanics by David J. Griffiths, and this book is highly recommended for you, so get a hold of a copy of this particular book, because this will help you in understanding the lectures. The topic for this lecture is on quantum statistical mechanics. So in quantum mechanics, we'll be dealing with a lot of particles, not just 1, 2, or 3, but in large numbers, like in the order of Avogadro's numbers. So at absolute zero, a physical system is in its lowest energy state. But as we turn up the temperature, random thermal activity will happen, and then some of these particles will go to its excited states. And then we ask, if we have a large number n of particles in thermal equilibrium at temperature T, what is the probability that a given particle would be found to have an energy Ej? Here, the probability in question has nothing to do with the quantum indeterminacy. Exactly the same question arises for classical statistical mechanics. We are looking for a probabilistic answer because we're dealing with practically a large number of particles. So here, if we have, then we could not possibly expect to keep track of each one or each of the particles separately. So I'll just read the second bullet. The fundamental assumption of statistical mechanics is that in thermal equilibrium, every distinct state with the same total energy E is equally probable. The rise in the temperature results to random thermal motions that constantly shifts the energy from one form to another, and of course from one excited state to another as well. But the total energy is constant because it is fixed by conservation of energy. There is an assumption that this continual redistribution of energy does not favor any particular state. The temperature is simply to measure the total energy for a system in thermal equilibrium. So in this particular statistical mechanics of quantum particles, we introduce how to count the distinct states and whether these particles are distinguishable, identical bosons, or identical fermions, because these three kinds of particles have also different behaviors when it comes to occupying an energy state. Now, suppose we have only 3 particles, although we're going to generalize this later to many particles, but let's start with 3 non-interacting particles of mass m in one-dimensional infinite square wheel, And so of course these three particles will have total energy of pi squared h bar square over 2 ma square, na square plus nb square plus nc square, where the n's are positive numbers. The ground state of course would be n equals na equals nb equals nc equal to 1. But now for the sake of argument that the total energy of the three particles would be 243 pi squared h bar square over 2ma square, which is to say that the sum of the squares of n would be 243, and this happens like there are 10 combinations of numbers that can have that result. So for example, all three could be 9. So you have 9 square plus 9 square plus 9 square would be 243. Or 2 could be 3 and 1 could be 15. And the other one combinations are 1 could be 5, 1 could be 7, and the other one could be 13. So there are 10 combinations of positive integers that can do that. So we have them here. This one, these 3 ones here, and the 6 ones here. So the state with the most probable combination is this one for distinguishable particles. So if the particles are distinguishable, each of these 10 states have the same probability of existence in thermal equilibrium. We're not really interested in knowing which particle is in which state, but we're mostly interested on the total number of particles in each state. This means to say we're interested on the occupation number n of n for the state phi n. The collection of all occupation numbers for a given 3-particle state, we call that the configuration. So if all the 3 particles is in the state psi 9, the configuration would be this one. There are so many states, but all the 3 particles are in the state psi 9. So here you have n of 9 equals 3, and all the rest are 0. That means there are no particles in other states. All the particles stays at psi 9. We could also check on the configuration of particles where 2 are in psi 3 and 1 is in psi 15, for example. This is supposed to be psi 15. So the configuration would be 0, 0, 2, and then you have succeeding that would be 11 zeros, and then you have 1. Then the rest would be 0. So this is your configuration for that. And then if you have one particle in psi 5 and one particle in psi 7 and the other one would be in psi 13, the configuration would be this one here. So this will be n5 equals n7 equals n13 equals 1. So the third one is the most probable configuration because it can be achieved in more ways than the first two. Like the first one can only be achieved in one way, the second one could only be achieved 3 ways, but the third one could be achieved 6 ways. If one of these states or one of the, if we select one of the 3 particles at random, what is the probability Pn of getting a specific allowed energy En? So for example, if we select energy, say for example 1 pi squared h bar squared over 2 ma squared, the probability of that would be 0. But how about getting a particle with energy E9? So what would that be? So in that case, you have a particle that should be in the first configuration, and that first configuration would give you only 1/10 as a probability of occurrence of that particular configuration. But there are 3 of the particles which gives you energy of E9. But out of the 3, you will get a probability of 1 of having E9 because all of the 3 particles have energy E9. So that's 1/10 times 3/3. So that gives you a probability of 1/10. The chances are 3 in 10 that the system is in the second configuration. So you will have, in this case, the probability of getting E3, for example, is, for that configuration, you have the probability of getting E3 is 2/3. And the probability of getting E15 is 1/3. But that occurs 3/10. The configuration occurs 3/10. So you have to multiply 3/10 times 2/3, and that would be 1/5 for a particle of energy E3. And then for particle of energy 15, then that would be P15 equals 3/10 times 1/3. That would be 1/10. And for the most probable configuration, you have 6 in 10. You have an occurrence of 6 out of 10. So you can get the probability of getting a particle of having energy E5, E7, or E13 would have 1/3 for each. So if you want to get a particle with energy equal to 5, or E5, then that would be 6/10 times 1/3. and that would be 15. So if you add 1 over 15 plus 1 over 10, so this would be this one is 1 over 5, I'm sorry. So this would be, so for getting P5 you have, so for this is P9 plus P3 plus P15 plus P5 plus P7 plus P13 should be equal to 1. This one is 1/5, 1/5, 1/5, so this is 3/5, and then you have this also 1/5, so this is 4/5, and this is 1 over 10 and 1 over 10, so everything, the probability is equal to 1. So how about if the particles are identical fermions? The anti-symmetrization requirement, here we do not include spin yet, includes the first and the second configuration, which assigns 2 or worse still 3 particles into the same state, and of course that does not count in fermions. So you only have a state where there's only 1 particle per energy state. So the only configuration that would exist for identical fermions would be this one here. And then of course you will have P5 would be 1/3, P7 would be 1/3, and P13 would also be 1/3, because like the second configuration where 2 particles are in the same E3 state, and in the first configuration where 3 particles are in the same E9 state, cannot exist when the particles are fermions. So they exist, the third configuration is the only configuration that exists. So how about when the particles are identical bosons? The symmetrization requirement allows for one state with each configuration, because like for the third configuration you don't know which boson is which, so only one particular configuration for the third one would exist here, and of course only one for the first state as well, and only one for the second state. So for the first and the second configuration, so for the first configuration you have one particle there is you can get one P9, that would be 1/3, the probability of getting a particle with energy E9, that's P9, and that's just 1/3 because there are 3 particles with energy 9. And then for the second configuration you can get a particle with energy E3, and that would be just 1/3, because this is the occurrence of the configuration, and then the occurrence of the particle with particular energy in that configuration. So you have to multiply that, so that would be 2/9. And then for particle with E15, energy 15, so this is the occurrence of that, this is the occurrence of the configuration, and then you have the occurrence of the particle in that particular configuration, so that's 1 over 9. And then you have, of course, for P5, P7, and P13, they would be the same. So the occurrence of that configuration would be 1 over 3. And then you have, for the occurrence of each particle, would be 1 over 3. So that's 1 over 9. So if you add them all, this is like 1 over 9 times 3 would be 1/3, plus 2 over 9 plus 1 over 9 plus 1/3. They would sum up to 1. So here's the purpose of this example, is showing you how the counting of state depends on the nature of the particles. So if they're distinguishable, the probabilities are different. If they're fermions, the probabilities are also different. And of course, when they are bosons, the probability is also different. So now, how would we generalize this to a huge number n of particles? We're just dealing with 3, but it's already complicated. But how about dealing with large number of particles? So for a large number of particles, the most probable configuration becomes overwhelmingly more likely than its competitors, so that for statistical purposes, the other states, which occurs with very small probabilities, can be ignored. And the distribution of individual particle energies at equilibrium is simply their distribution in the most probable configuration here. So we will now go to the general case. So if we now consider an arbitrary potential for which one particle energies are E1, E2, E3 with degeneracies D1, D2, D3, there are Dn distinct one particle states with the same energy En. That's the meaning of degeneracy, meaning that there are in a particular E1 or in a particular En, you can put many particle, you can have also many degeneracies. So in the example, the degeneracy was only like 1 for each. Like for the first configuration in the example, you have a degeneracy of 3. You can put 3 particles, like fermions, for example. You can put 3 particles in that particular energy state with 3 particles, because those are that is a degenerate energy. So meaning there are 3 rooms in that particular energy state. So the situation is that if we have n particles, and so the configuration would look like this now. There's so many. So there would be n1 particles in state of energy E1 with degeneracy of D1, and n2 would be the number of particles with energy E2, and of course degeneracy of D2, and so on. The question is, how many different ways can this be achieved? Or more precisely, how many distinct states correspond to this particular configuration? So we denote the answer as qn of n1, n2, n3, and so on. And this depends on whether the particles are distinguishable, again, identical fermions or bosons. So the first one, we assume the particles to be indistinguishable. So here we have to take note that the total number of particles, so we have n particles, and this is supposed to be the total number of particles in every state. So you have n of n here, and to n, or n. Say if you have you can also put right there an infinity, for example. So if we assume that the particles are distinguishable, then you can put n1 particles in state E1 or energy state E1. So here actually the answer is this one here. The binomial coefficient is the answer. So let's investigate more of this in detail. So if there are n particles, then for the first bin you will have n ways to pick the first particle, because there are n particles. So that leaves you n minus 1 for the second particle, and so on. So this one is this is the number of ways you can pick the particles for energy state E1 here. So until you reach n1, because there are n1 particles in the energy state E1. So here, let's go back. Now you now go to the second energy state. So in the second energy state, you're only left with n minus 1 particles. So that's now a different counting for the second energy state. But for the first energy state, we have n1 particles, but there is also a permutation of that particle, because you can put for example, n1 is like 15, for example. So there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 particles. So what if we put 15 first, then 12 second, then 10 the third, and fourth would be 8. So it's also different from putting the first particle to be the particle, the fifth particle, and then we put the seventh particle the next, and then that would be different from that arrangement will also be different. So we have to consider this permutation as well. So that means we have to divide this n factorial by n1 factorial. because we don't care about the permutation. We just cared about how many particles are in energy state E1. Now, how many different ways can those N1 particles be arranged within the first bin, or the first energy state E1? In that particular energy state, there are D1 states in the bin also, because you have degeneracy D1. So evidently here you will have D1 to the N1 possibilities. So you have an energy state E1, and that E1 can accommodate as much particles, N1 for example, but then the N1 particles can also occupy the different degenerate energies in that particular energy state. So you have to multiply D1 to the N1 in that counting. So you have to multiply D1 to the N1 here, such that for the first bin, or the first energy state, you will have here. Now, in the second bin, or the second energy state, E2, you will have, what's left in the particles is N minus N1, and so of course with that number of particles being left, you will have here, you will have this one here. So instead of n factorial, you will have n minus n1 factorial d2 to the n2, and then you have the denominator of that would be n2 factorial times n minus n1 minus n2 factorial. And so you'll be left with the next one would, for the third bin, you'll be left with n minus n1 minus n2. So this kind of term will recur, provided that you have the correct term for the next number of particle that's left from the original number of particles. So your number of particles, or your Qn, would be this much. You have to multiply for the first bin, the second, you multiply for each of the bin, the probability, the number of occurrences, this one, and so on. So you will have this one will cancel with this one will cancel with that, and so you're only left with this term here. So this is for distinguishable particles, but for fermions, of course, these are identical. They are indistinguishable and they only occupy one state. So it does not matter which particles are in which state. The anti-symmetrization requirement means that there is just one n particle state in which a specific of one particle states is occupied. And also, only one particle can occupy any given state. So, there are dn ways. Here is, this is the formula to get the number of number of counting for the first bin. So by the way, this is just dn factorial over n of n factorial dn minus n factorial here. So for n1 you have for the energy state E1, you will have n1, and then this n1 should be arranged in d1 degeneracy. So n1 should be, in this case, n1 should be less than d1. So if it happens that or n1 should be less than or equal to d1. So if n is greater than d, then it's assumed that that configuration is restricted, because you cannot put one more particle in a particular energy. It's only one particle for each degenerate energy. So if the degenerate energy would be 5, so n1 would be only 5. You cannot put 6 or more. So this is for fermion. It's a lot easier than the distinguishable particles. But for bosons, it's a different case as well. So here you have n particles. So, but in energy state E1, you can have there n1, but this n1 could also choose which degeneracy state, degenerate energy state they would like to occupy. So that's the problem here. So how many different ways can we assign n of n identical particles to dn different slots there in that particular energy state? So in this example, say for example you have dn equals 5, an arrangement for 7 particles would be 2 for the first, so this is for example d1, this is d2, d3, d4, and d5. So 2 could be in the first degeneracy state or degenerate state, 1 could be in the second, and 3 could be in the third, or in the fourth would be 1. But could also be that this is only 1 here, 1 also here, 2 here, for example. Say for example you have 1 also here, and then the other 2 would be here. So that's also a configuration, I mean an arrangement that could happen in energy state E1. However, we're not really interested with this arrangement, but we can still count these as an arrangement for energy state E1. So here, by the way, the dots represent the particles, and the cross here represents the partition of the different degenerate states. So there are only, if there are 5 degenerate states, then there would be 4 partitions. So you have 1, 2, 3, 4, 5 degenerate states. So there would be n plus dn minus 1 different ways to arrange the particles. So, but by the way, the dots and even the crosses are all equivalent. I mean, the dots are all equivalent because they are identical bosons. You don't know which particle is which. And of course, the crosses are also equivalent because the energy are the same in each partition, but the arrangement would be of course different. So there are n plus dn minus 1 factorial number of configurations, but you have to divide it with the permutation of n and also the permutation of the crosses. There are, of course, the partitions. There is dn minus 1. So the number of configurations would be this one. So let's now get the most probable configuration. So for these particles, for these kinds of particles, we assume that the number of particles does not change. This means that n is just the summation of the particles in energy state E1, which is N1, and for E2, which is in N2. And so if we add them, it will just give this the total number of particles. And of course the energy would also be can also be summed there. Again, in thermal equilibrium, every state with a given total energy E and a given particle number n is equally likely. So the most probable configuration N1, N2, N3 is the one that can be achieved in the largest number of different ways. It is that particular configuration for which Qn is a maximum subject to the following constraints. If we have some constraints, then we have to use the Lagrange multipliers to find the maximum of Q. So by the way, you can write these constraints using the Lagrange multiplier technique. This is like this constraint can be written as n minus summation of n equal, so that's equal to 0, and this one is also E minus n summation En equal to 0. So these are the constraints that you have to use. So when you want to maximize or even minimize Q, then the technique would be using the Lagrange multiplier. So if you want to get the maximum of this function, then with subject to the following constraint, this one and that one, then you can write a new function where the sum of the functions would be f, like f here, and then you have to multiply a Lagrange multiplier for the first constraint and for the second constraint and for the third constraint and so on. But in this case we only have two constraints, so our general function would only be this 3 here. And then you have to set all the derivatives equal to 0 here, and for the Lagrange multipliers as well, 0. And we're only look here, our Qn is dependent on n of n, so we can get the derivative with respect to n of n, and of course we have the Lagrange multipliers. This should be equal to 0, and g with respect to lambda would be also equal to 0. So for this, our function would be here, g. By the way, we use L and Q because it is easier to work. The logarithm of Q is easier to work because it turns the products into sum rather than multiplying big numbers. So you have L and Q. It doesn't really matter, we can get Q later on, but here you have L and Q, and then you have the Lagrange multiplier alpha and beta, and these are the two constraints there. So if we get the derivatives with respect to alpha and beta, we'll just get the constraints, so it's okay. What matters here is the derivative with respect to n of n. So we can start with distinguishable particles. Here. So what is the Q for distinguishable particles? We have, this is so the Q would be for distinguishable particles, this is Q equal to n factorial, the product of n times and here would be dn n to the n over n over n factorial. So if we get the ln of Q, we will have to also get the ln of this side. and that would be equal to this one here. So we now get the derivative of g with respect to n of n. And by the way, we have to use the Stirling's approximation. This approximation works for very large number z. So this is now the Stirling's approximation here. But this also works for z equal to 0, for example, but the approximation works for z being a large number. And of course we're going to use this approximation because we're dealing with a large number of particles. So we can write that g into this one here using the Stirling's approximation, and that our partial derivative of g with respect to n would be now this, and this should be equal to 0 to get the maximum of g. And so our most probable occupation number for distinguishable particles are here. So for E1 you can get D1 and N1, or you can get N1, I mean. So for fermions here, Q is of course given by d factorial over n factorial minus over n factorial times dn minus n factorial. So you will have your g to be equal to this, and then you will have, for again you have to use the Stirling's formula, and you will have your n to be equal to this one here for fermions. And then for bosons, again you have to use the Q for boson, which is given by this equation here. So let's just look back in order that we familiarize ourselves with the Q. So this is for the boson. So what's actually important here is the result, not the details, but of course we have to know how the results were arrived. So for the bosons you will have so this is for the bosons. Your Q is given by that expression in equation 5.76. You can review the video later on what's the equation. So your G would be looking like this, and then if you get the partial derivative with that with respect to n, and then equating that to 0. We equate this to 0. So you will get the most probable occupation number for bosons to be this one. The one in the numerator can be dropped because dn is also a very large number, so that can also be dropped. Now, what are the significance of the multipliers alpha and beta? By the way, beta would just be a multiplier related to energy, and alpha is a multiplier related to the chemical potential. So let's go back to the three-dimensional infinite square whale. So the energy allowed for that case is this one, where the K is equal to this. And going back in the discussion, we have the degeneracy. We actually treat here K to be a continuous variable. If we go back to the discussion, the degeneracy there is equal to this one. And then of course we have N. If we substitute this dk and energy to here, say for example in this particular N, so we substitute dn with dk, and then the dn here, and this en is substituted with ek, given by this, and dk here. So we will have n to be an integral of course this v over 2 pi square e to the alpha. I mean the v over 2 pi square is coming from this k here, and so I mean from dk here. So you have e to the alpha is equal to this one. So what is alpha there? You can get alpha by getting the ln of this side and the ln of this side also on the other side. So for the energy, you can also get the integral using equation 5.78, the second constraint. Now we have E. If we substitute, or if we use 5.97 here, this expression for E alpha, we can get the energy. Regardless of the spin, this result is correct. If you recall back in your statistical mechanics, there is a classical result equal to this as well. So when you compare these two equations and that, you can see that the beta is just actually equal to 1 over kBt, where kb is just the Boltzmann's constant and T is the temperature in Kelvin, the temperature of the system of particles. So this is actually true even if the particles are fermions or bosons. It's still the same. This is for distinguishable particle result, but it is also true for fermions and boson. And it is also customary to replace alpha with the chemical potential. Here. By the way, so we can write this as mu of T is equal to, or shall I just write it as mu equal to some negative alpha over beta. So that we can write so we have this following one particle state with energy epsilon. This is just the n here is just equal to n over the degeneracy. So this is the Maxwell-Boltzmann distribution for distinguishable particles, the Fermi Dirac distribution for fermions, and the Bose-Einstein distribution for bosons. So look at here. As the temperature goes to 0, this quantity here is going to 0 if the energy is less than the chemical potential. The chemical potential is, negative, for example, because or positive, and if epsilon is negative, or if it is positive, then it will go to infinity, and of course you will have Ne there, just 1 or 0 in this particular energy state. It's either, so if the temperature goes to 0, then all the states will be filled up. So, by the way, the chemical potential at absolute zero is precisely the Fermi energy here. So let's look at the Fermi-Dirac distribution for t equal to 0 for t and for t somewhat above 0. So you have here this one. So you can only have one or 0 here. And your EF there is the transition energy from which a state is to be occupied or to be emptied here at this point. So for distinguishable particles in three-dimensional infinite square well, the energy is given by this. And of course, when you manipulate equation 5.97, we'll also get the chemical potential to be this one. So you can also get the formulas for fermions and bosons by using equation 5.90. You can review the video to get the equations 5.90 and 5.94. So here we have the N for bosons and fermion. It's only differs in sign in this particular factor in the integral. Also here the energy. So you can do some problems. You can derive this from the constraints, and then you have to just get the statistical distribution for bosons and fermions. Now we've come to a special case in quantum statistical mechanics we call the black body spectrum. This is just the radiation that is emitted by a hot object, and this radiation is purely because of the heat of the temperature of that object. This radiation is not visible to the naked eye, and this is called the black body spectrum or the black body radiation. So photons are bosons, but what makes them different from the bosons that we discuss is that these bosons are massless, and of course these are relativistic particles, which is not included in our discussion. And also the energy of the bosons, of the photons I mean, is energy h omega, and the wave number k is this one, involving the speed of light. And there are two spin states for the photon. The spin of the photon is 1, but the zero state, spin state, or 1 0 does not exist. And the thing with photon is that these particles, they decrease in number when the temperature is low, and they also increase when the temperature is high. This means that the constraint on the number of particles, the n, summation of n of n, would have to be neglected, you have to be ignored. That means alpha, the Lagrange multiplier for that, would be 0, or we can set that as approaching to 0. So if you do that, you'll be able to get the most probable occupation number for photons, which is this one. And so you also have the degeneracy, but you have to multiply by 2 because there are two spin states. That's why the 2 here disappears, because of the two spin states of the photon. And then you can get the energy density, this one here, to be just the rho here. And if you plot this one with temperature, and frequency, you will get this curves. And so for example, at 2000 Kelvin, you will have the energy density at maximum here, and for 4000 Kelvin you will have it here. And of course, but as the temperature goes high, the maximum, or I mean the maximum energy density is going nearer and nearer to the visible region. But this one here is the black body spectrum. It's not visible to the naked eye. So that's it for this chapter. We will be doing a Q&A on this. So I hope you've already written your questions as you listen to this lecture. So the next lecture would be on chapter 6. So see you in our Q&A.